The broadcast is now starting. All attendees are in listen-only mode.
Hello everyone, thank you for attending today's webcast titled Finite Element Analysis FEA with Autodesk Inventor, presented by Kendra Cooper, Solutions Engineer with Hagerman Company. We also have Forrest Judd, who's a Solutions Engineer with Hagerman, on the line to assist with your questions. A few housekeeping items: this presentation is being broadcasted in a listen-only mode. You can ask questions by typing them into the question section of the GoToWebinar control panel on the side of your screen, and Forrest will address your questions throughout the presentation. At the end of the broadcast, when you exit GoToWebinar, you'll be prompted to fill out a short 3-question survey. We ask that you take a few moments to provide us with your feedback. Also, all attendees will receive a certificate of attendance and a link to the recording of this presentation. Kendra, whenever you're ready, you may begin.
Thank you, Bradina. Hello, everyone. I've got a slide up here just to guide everyone into the meeting for the dial-in information and the access code. Again, as Bradina stated, we've got Forrest running the background questions. We will have time designated at the end to address those specifically, but he will also address them as they come in. So we'll go ahead and get started. This particular slide is just for the individuals who may not be hearing me right now. Hopefully everyone does. And to address those that can hear me right now, if you have any questions, if you look in the meeting manager, you do have a questions area to submit your questions, again, at any time, but we will designate time at the end to address those. And of course, if you have any kind of audio difficulties, video difficulties, anything that pops up, that's an ideal place to put it in to let us know what's going on, and Forrest will try to help you out. So we'll go ahead and dive into this. Welcome to today's presentation on Autodesk Inventor FEA, Finite Element Analysis. Again, my name is Kendra Cooper, MCAD Solutions Engineer. I am stationed in the Knoxville, Tennessee office, and we have Forrest Judd, also an MCAD Solutions Engineer, and he's stationed in one of our California offices. So we've got you coast-to-coast coverage today. Before we get too far into this, I want to submit a poll question to everyone. And the question is, do you currently use Inventor Professional? And if you can go ahead and answer that, give a yes or no answer. If you're using the stress analysis tools out of Inventor Professional, go ahead and say yes. That'll give us an idea of what kind of audience we're looking at today, some of the users that are out there and what they may be benefiting from the software. So it looks like we're almost 50-50 on that. Looking at about 90% of you have voted almost. We'll give it just a couple of seconds more, get a few more votes coming in. So we're looking at about 56%, 55% saying yes, 44% saying no, that you do not currently use the Inventor Professional tools. So now I've got to see 92% voted. I'm going to go ahead and close this poll at this time. And I want to share those real quick with everyone. So you can see that we've got, out of the 93% of you, it's almost a 50-50. And that's pretty good. That means a lot of you have the tool set in front of you. You are trying to use it. Hopefully it's fitting your applications very nicely. If not, we can discuss that option later. For those that are not currently using it, don't know if you have Pro or not, but hopefully today you walk away with some insight of how Inventor Pro, specifically the FEA portion, can help you and help your design process. So we'll go ahead and get back to the presentation. What we're looking at here is just a general overview of where the product design suite packages can help you out. They can start by helping you in the initial design areas for sketching, getting your idea from a napkin into the computer, laying it out into parts and assemblies, doing some motion analysis, some range of motion, doing the FEA to make sure it's going to be strong enough and hold up to some of the loads and constraints and movements you may be applying to it. And then also documenting your design with the drawing environment. You're covering everything from design engineering sales and marketing, into the production environment, and testing and validation. And all that comes in the product design suite package. It comes into the higher ultimate flavor of the package to get the full wheel effect here. So specifically looking at Inventor, just kind of a quick headline type of situation. With Inventor, you can cover all the bases. You can go from the initial design, you can go into building your parts, building your assemblies, putting all the components together. You can create visualizations of that. We're talking high-definition renderings for still images or high-definition renderings of animations, so you can show how the product works and functions and moves. And then you can also do the simulation with the FEA portion and the kinetic analysis portion as well. So again, Inventor 2015, you're getting a lot of tools in here. It's parametric controls, but you're also getting some freeform modeling tool sets now. That was new with 2015. You can work with the design how you wish to work with it. It's very flexible. It works with just about any 3D file format out there. We can bring in Pro-E files, SolidWorks files, Solid Edge files, CATIA files. You've got a lot of flexibility of what kind of information you can get from outside of your department or outside of your station to work with and create your parts, assemblies, and designs. Specifically looking at the Inventor Professional area. With Inventor, there are a lot of what I would consider sub-environments inside of Inventor. Take, for example, sheet metal. In a sense, it's kind of a sub-environment. It has some different tool sets that are unique to sheet metal design, and some of these others fall right into that classification. The frame generator. It is a set of tools that is unique to designing framing. The frame members in Inventor are more or less intended for small structure, not talking like a house or an addition onto an office building, but we're talking something like the framing for a large piece of CNC equipment, or maybe framing for some kind of overhead trolley system, truss work, things like that. Can you go ahead and design framing for a building? Yeah, I mean, it's not going to have a limitation on it that you can, but it's not the ideal tool to do that with. So with the frame generator, you're sticking with smaller scale structures. You also have the cable and harness routing system in the professional module. That allows you to do point-to-point cable and wire routing, and you can map those or route those to a harness in a 3D environment. So when you do that, now you're given a cut length of the wire. You know exactly how long that wire needs to be to go from point A, run around this pole and through this harness and over this hump and around that fan and connect to point B. You can get that length from that 3D environment. The tube and pipe routing, much the same as the cable and wire. You're routing from point A to point B with various types of tubing and fitting connections. You have butt welded pipe, you have threaded steel flange pipe, you have flexible hose connections that you can do. A lot of wide range of tubing and piping connections. You also get plastic part design if you're doing any kind of injection molding. You have full control over the tooling that you're going to be using, the mold and core, the separation, the gating, the cooling system, the runners. All of that is built into the tooling module. And again, like I've mentioned, sheet metal, it's another module. It's not particularly unique to Pro, because you do get sheet metal capability in every version of Inventor, but with the sheet metal, it's got a unique set of tools for making flanges and doing cuts and doing bends and lofted flanges and rolled flanges. And there's a lot more in there too. That's just a quick overview. For today's presentation, we're talking specifically about Inventor Pro's FEA or simulation section. With the simulation section, it's really threefold, not just twofold, because you have FEA, which has two subsections in it. You can do static analysis or you can do modal analysis. And then sidebar for FEA, you can do motion analysis with dynamic simulation. So you're getting the motion simulation. You also have framing analysis that comes into that. You have the FEA, and then also the plastic injection molding, because we can simulate the fill time, the cooling rate, weld lines, and air traps for plastic injection. Lastly, before we get too far into the FEA, with all of this data that you're going to be working with, you need a good file management system, and that's where Autodesk Vault comes into play. It works directly inside the CAD software. You also have a standalone client interface for it, and the biggest thing we hear from customers as to why they use Vault is not per se to store and organize their stuff, because as best as we try to organize it, it doesn't always stay organized. The beauty about Vault and what most customers use it for is searching, because all of the property information for your Inventor files, your part files, your assemblies, your drawings, AutoCAD drawings, PDF documents, Word documents, AVI files, JPEGs, any of those file formats, you can add those into Vault, and those file properties come in with it, and you can search on all of those file properties. So it gives you the flexibility to search for certain job numbers that also deal with a particular customer in a particular state done by a certain designer. You can do a combo search for all that and find those files specific to that search criteria. There are multiple flavors of Vault, from basic to workgroup to professional. As you step up through the flavors, you get more capabilities such as lifecycle management, setting files that are work in progress versus pending review or release. Then when you go higher, you also get into revision controls, you get into item controls, and even linking up with company ERP systems. To talk about product design suite, there's two main flavors, the premium and the ultimate. And with premium, you get Autodesk Inventor. You also get AutoCAD and AutoCAD Mechanical. A lot of people don't realize you get two of those, the two individuals. You get some other tools such as Recap. You get access to Vault Basic, Navisworks, and 3ds Max. With Ultimate, you essentially upgrade your standard Inventor and you get the professional module. So you're getting the tube and pipe routing, the cable and wire routing, the simulation, the injection molding. All of that comes as part of the Pro flavor. You also get AutoCAD Electrical and Navisworks Manage. So to talk about the stress analysis, there are some assumptions you need to make when you're using Inventor Pro to work with your stress analysis. Those assumptions start with the deflection and the stress are linear. The analysis that Inventor does is linear only. What does that mean? A lot of people may not realize what the linear loading or the linear phrasing means. So as you apply a load, there's a particular amount of deflection or deformation or movement in the product. If we can all envision a diving board made out of metal. As you apply 500 pounds on the end of that diving board, it deflects downward towards the pool whatever amount. As you apply 1,000 pounds, it deflects more. 1,500 pounds deflects more. And as you plot those points on a graph, you will get a straight line. That is your linear form. And the reason it's linear is dependent on various things, but mainly is the material that you're working with. So the vast majority of your metals are going to be linear for most of the part. Even wood material can be linear in a very small area, but when you deal with plastics and polymers and rubber materials, no, those go into a non-linear classification. So what does that look like? The nonlinear graph, if you did the same thing and the diving board was made out of plastic, 100 pounds would deform it X amount, 200 pounds deform it a higher multiplier of the first amount maybe. It wouldn't be, as you started plotting points, it wouldn't be a straight line. It would actually curve. And it could even curve not just up, but even return and come back down. So because there's not a straight line, you're dealing with a non-linear analysis. On any kind of material that's non-linear, again, plastics, rubberized materials, polymer materials, and again, wood, we have, some cabinet makers and furniture shops, and they want to look at, building chairs or tables or shelves or anything to hold certain weights. They can to a point, because wood does have linear progression to a very small point, and then beyond that it becomes nonlinear. So you can look at the material that you're working with and what's happening to it, and if it's one of those nonlinear materials, then Inventor is not the tool that you're going to want to use for that, because you get into very unpredictable results. So you want to stick with linear loading, linear materials only. More specifically, where are we looking in that line? So even back here in the nonlinear plastics area, that curve, there's going to be a portion of that curve that could be straight, and it may very well be a very small portion of that curve. But in that straight line area is where we can look at analysis, and with we can look at using Inventor for the analysis. And with that straight line area, we're confined to that. Once it gets beyond that yield tensile strength, it starts to curve. You get into that plastics deformation region, and you're barking up the wrong tree. You need to look at another type of analysis tool that we offer. Some of the key points when you're looking at, is Inventor the right tool to use for this type of analysis? First and foremost, the loading should be static, and it should be applied slowly. There should be no sudden loading and no impact loading. Also, another big item, temperature has no effect on the material properties or the part geometry. That's a pretty big one right there. If your metal bracket or something is being subjected to massive amounts of heat, that's going to change its failure rate. It's going to change where it fails, how it fails. So temperature needs to have no effect on it. The deformation, the amount of deflection that your part or assembly is undergoing or realizing, needs to be small, relatively speaking. Now, there's no good numerical factor to give you. You can't say, well, it needs to deform less than a ½ inch. Not going to work that way, because it depends on a lot of various factors. If you've got a part that's 20 feet long and you're putting a weight of 10 pounds on the middle of it, it's going to bend a little bit. That's fine. But if you're putting a weight of 5,000 pounds on the end of it, depending on what that 20-foot piece is made out of, if it's something like aluminum, that can be a large amount of deformation, and you may get some far-out results that you can't really trust. So you have to kind of look at the deformation being very small. Also, no buckling strains in the analysis. Inventor doesn't handle those types of calculations. You need another product that we offer. You want to look at some of your goals. What's your main focus to get out of this analysis? Are you looking at the amount of deflection? Are you looking at the amount of stress or possibly vibration? Because again, we can do modal analysis with Inventor's FEA. You want to determine how your geometry interacts with the environment, and that goes into how is this bracket fixed? How is it attached? And when it's attached, where are the areas that it can move, that it can flex and bend? And that gets into your loading location, how much load you're putting on it for your magnitude, and then how you have it constrained. You also want to make sure your model is ready for analysis. And when I say that, I don't mean that you've modeled everything under the sun related to it and you're ready to just throw it in there, throw a load, fix it down, and go. What I'm referring to is there's a lot of things on a piece part, for example, that may add computational time but have no effect on the end results. Fillet radiuses are notorious about this. A lot of times they won't have any effect, especially if they're in the area of the model that's not even being loaded or constrained. So you can, if you leave those features in there, then it can add to the cycle time for the analysis. If you suppress those features, it can speed the analysis up, and the results are usually not effective. You also can do this in an assembly. So you may have a lot of parts in the assembly that, again, will have no bearing whatsoever on the effectiveness of the assembly or the results. Bolts, nuts, pins, washers, notorious items for not affecting the end results. Sometimes it is the case. Sometimes they can affect it. You have to really look at the situation to determine that. But in most cases, they don't have that much of an impact, if any, on the results. So you can take those and you can create levels of detail to where you have those turned off and use that level of detail in the analysis portion. And again, identifying unnecessary features, that would be your fillets, your chamfers. Even things such as holes that are drilled in it maybe to lighten the load, they may or may not have an impact over the overall strength. So you have to look at those individual features. The basic process for this is you're looking at creating your simulation. You want to watch your settings. You want to add your loads, and the various loads you can put in here are forces, moments, pressures, bearing, and body loads. You want to look at your constraints and add those carefully, and then contacts for assemblies. And when I say contacts, I'm talking about how two parts connect to each other. If you have two plates that are typically bolted together, I just mentioned that you want to turn off the bolts. You want to suppress the bolts to make the simulation run faster. You can put a contact or contact joint, if you want to call it that, but a contact between those two plates, and it simulates that bolted connection. In a sense, you're calling it a no separation contact, almost like a welded or glued contact. Once you have all of that set up, you're going to run the analysis, check out your results. You're going to run a quick sanity check. You're going to look for convergence. If you need to refine the model and make adjustments, you can do that, and then you have reporting tools to document the design. So let's take a quick look at what all of that looks like. So what I've got here is I've got a trailer hitch assembly, and you can see there's some details that are in here, some details that are not. Again, this gets into keeping things simple that don't need to be part of the analysis. In Inventor Professional, to access the analysis, the FEA tools, it's under the Environments ribbon, and you have your various pro modules spread out here. You've got your dynamic simulation for your motion analysis, your stress analysis for FEA, your frame analysis for FEA, and we'll briefly cover that a little bit later. You also have optimization, and if we have time, I'm going to get into this real quick. A lot of people aren't sure what this actually does for you, but I'll try to jump on that and give you a quick heads up on it. And then you have your cable and harness, tube and pipe, beam exchange, things like that. So I'm going to start a new stress analysis. I'm going to create a new simulation. Actually, I've already got one, but create one from scratch. Simulation type is going to be a static analysis. You've got some controls in here to apply motion loads from the dynamic simulator. You can run a modal analysis, set up certain contact constraints, things like gaps between faces. Anything less than this, it'll apply the contact and what type of contact it's going to be. So you've got some controls here. You can name your simulation, and this is going to be a single point simulation, but you can also do a parametric simulation where you give certain parametric controls. Let's say this plate is going to be, we're looking at this plate being a 1/2 inch or 5/8 or 3/4. Which of these three is going to see the least amount of stress with the least amount of weight impact and all that jazz? Get the most bang for your buck. So you can set up that parametric table design if you wish. Again, this is going to be single point. Takes me into the FEA, into the simulation portion. The main thing you want to start with, in a sense, you want to kind of read this like a book, going left to right. So I'll start with working on the materials. And if you already have all of your materials assigned in the piece parts, then you're good to go. But this is a nice, quick sanity check to come in here and make sure you've got all the materials assigned. You can see pretty much everything is a high-strength, low-alloy steel. If you don't want that material, or if it says default, you can do an override out of the material override column. So everything looks good there. Once you've had your materials set up, then you want to look at applying your constraints. You've got fixed, pin, and frictionless constraints. So with those three, I've got this set up exactly where we should be. Actually, I'll cover it a little bit later, so give me 1 second and I'll come back to that. With those 3 constraints, they're going to cover the basis for everything you're going to need. The fixed is going to lock it down. It's not going to move anywhere. So that could be to faces, to edges, to holes. With the pin constraint, since it's a rotational type constraint, it doesn't keep it from rotating, but it keeps it locked in on that center line, so it doesn't pull away from that center line axis. And then the frictionless is exactly that. It's able to slide along a particular planar direction, but not separate from that plane. A good example of this might be a machine that sets, a CNC machine that sets on the floor. If that machine's big enough and heavy enough, it's not going to bounce off of that floor. So you could put a frictionless constraint to lock it down in the floor contact. So with this particular assembly, one of the first things I'm going to do, looking at the design and all the features we have in here, I've got some bolts and nuts, and I've got a pin and a clip that I don't really need. I'm going to be fixing the assembly brackets back here and putting a weight on the hitch ball. And those bolts and nuts are not going to impact the overall strength of this assembly, and neither is the pin or the clip. So I'm going to take and suppress those from the analysis. So over here in the tree, you have access to all of the model geometry, all of the parts, and you can select those, just right-click on them, and you can exclude them from the simulation. They're going to kind of ghost out. So you'll see them there, but they look like they're made out of glass or they're kind of ghosted. So that takes your simulation time down dramatically. Once I have that done, I can look at applying my fixed constraints. I'm just going to apply those constraints to the 4 bolt holes where this entire hitch mounts to the vehicle. And the next thing I'm going to do is the loads. Again, as I said, you have forces, you have pressures, bearing loads, and torque loads or moment loads, and you also have gravity. And this is a good time to point out, if you're ever in doubt if gravity has an effect on your product or on your assembly, go ahead and specify it. It's never a bad idea to include gravity. You never know if gravity is going to have an effect. So you can always just specify gravity by picking a face or an edge and choosing the direction that gravity has a role. With this one, I'm going to apply 2 forces. So the first force is going to be to the top of the trailer hitch ball, and that's going to be the trailer itself bearing down about 300 pounds. The next force I'm going to apply is also to the trailer hitch ball, but this time I'm going to pick the spherical surface of the ball. And you'll notice the orientation kind of gets weird on me, for lack of a better word, but you can specify that direction by using a face or an edge to determine the vector direction of the force. So there I took that force and pointed it back. It's pulling back in the direction the trailer will pull. So for that, I'm going to put in probably the overall trailer weight pretty close to it. I think I'll put in 3,000 pounds for this one. And again, based on this direction orientation, you can actually turn it to simulate going around a curve when they're pulling the boat trailer or the flat trailer, whatever it is they're hauling on this thing. So I've got my fixed constraints. I've got my 2 loads that I have applied. The next thing I can look at is the contacts. Because this is an assembly, you have pieces that are in contact with each other that are mated up against each other, and you have various ways to look at contacts. You have a manual contact to where you can come in and specify the contacts between faces and between parts. And that allows you to control, okay, is this a bonded, like a glued or a welded or bolted type connection, or is there a degree of separation between these faces? Or maybe you have a sliding behavior, like almost like a frictionless, but not quite, but a sliding behavior, but the faces do not separate. So you have various contacts that you can create, and again, all of these are manual, and you just pick your faces or your edges that they are applied to. The other option is automatic constraints, and it will run through an analysis. It did that when I started the manual, actually, and it applied all of the contacts that it found as bonded contacts. And with the bonded contacts, you can roll through this and you can see each one of the contacts as it affects the different parts. So you've got a bonded contact between those two parts, between those faces. Same thing on the other end. You can kind of roll through to see if these contacts make sense or if they're completely wrong. So looking at the next step, you also have thin bodies, which I haven't talked about that. I'll come back later to talk about that. The next step in this process is looking at the actual mesh. So a mesh has to be generated for the analysis to run. So when I look at this mesh, just using the automatic settings, you've got control over the average element size, the minimum element size, the turn angle for the meshing when you look down in here at the actual mesh details, how the mesh will conform and turn around surfaces. You'll also notice on curved surfaces, it doesn't apply the curved meshing. It flattens it out. And this actually helps to shorten your analysis time. So looking at the mesh density, in certain areas you're going to have a higher density. In larger areas where there's no kind of geometry change, the density is going to get less dense. And that's exactly what you want. What you want to look for in the mesh, though, is you don't want a high concentration of a mesh where there doesn't need to be one. So looking around this bolt hole, you don't want to see this kind of meshing out here in the middle of the frame. That would be a bad sign. You could have a stress riser at that location. The other thing we'll look at a little later is convergence settings. With the convergence plot, when you're doing a simulation, you want the results to converge. You want very little change from one test to the next. And you can come into the convergence settings and set up your minimum number of H refinements so that you can see that convergence plot. Now that I've got the mesh view set, I've got the material assigned, the constraints, the loading, and the contacts in the mesh, I'm ready to actually run the simulation. So when I click on Run, it'll take just a few seconds for the simulation to run. And part of that reason is because I came into the assembly and I disabled or removed the bolts and nuts from the analysis. So my analysis is done. I'm looking at the von Mises stress results, and I can see my highest stress is 49 KSI. And that's actually, you can probe it if you want to, picking parts on here to see what the stress is in that location, just various locations you want to pick. So right there, I'm not even close to seeing the high stress. I'm about halfway there. So if I want to see the maximum, there is a display maximum and display minimum option. So if I look at the maximum value, it shows me with the flag coming out here where that maximum stress is being seen, and it's right there at the base or the washer face of the ball hitch. That's where the most stress is being seen. And it looks like this thing is failing based on how it's bent down and getting real distorted. But we can look at first and third principle stresses. We can also look at displacement. And when I look at the displacement, I'm seeing that it's bending down about 1/16 of an inch. And that doesn't really sound like a whole lot, especially for this overall hitch. The other thing you want to look at, especially with this design, if I look at it from the side, yeah, it's bending down, looks like it's failing, but what I'm also seeing based on the original shadow outline that you see here, the overall angle is bending up. So in a sense, the entire bracket, the mounting, and the main channels of this boat trailer hitch, or this trailer hitch, it's trying to counteract the load that's being put on it. And that may not be what we would expect to see, but if we go out and look at it in real life, that's what we'll find. So this is actually evidence of a pretty good design, a pretty solid design. As you're putting the load on it, at least this amount of load, the 3,000 pounds and the 300 pounds, as you're putting that amount of loading on it, the overall assembly is counteracting those forces to an extent. So let's jump back in here to the presentation real quick. Some of the guidelines that I took, you can segment the assembly, you can cut your assembly up into smaller chunks, smaller groups of assemblies, maybe even sub-assemblies if it's applicable. I did not have to do that with this particular one, but on the second item and third item, yeah, you want to look at suppressing features that don't affect the results. like cosmetic chamfers, fillets, things like that, features that are in non-critical areas. That goes back to the bowl holes that you may have, or the holes that you have drilled just to lighten the load of that part. They're probably not going to affect that part if that part is not seeing any kind of force or reaction or constraints. So you can suppress those and get an even faster analysis time. And then excluding unnecessary parts. That's where I suppress the bolts and the nuts. On the constraints, again, quick covering on the fixed constraints. The fixed constraints will stop your translation of that part or that face or that edge, really, not the part, but that face or that edge, in one, two, or all three directions. And you can enforce displacement using components, using that fixed constraint. The pin, like I mentioned, it prevents any kind of cylindrical surface from moving relative to that centerline axis. The frictionless, again, it's going to slide along a planar direction. It's going to slide freely like it's been greased, but it will never come away from that plane. It will never separate from that plane. When you're applying loads and constraints, you want to avoid applying those to any vertices or edges if possible. Even though you can select edges, by applying it to an edge, your stress could go through the roof and not really be a good indicator of what's happening in real life. You can also use commands like the split command to break up surfaces. A good example of this is when you have a bolt that is going through a plate and a force is pulling on that bolt. When you apply a load to a surface, the way Inventor applies that load is it applies it uniformly to that surface. So if you pick the top of that plate, the entire top of that plate is going to see that load. In reality, the only area that's seeing that load is what's underneath the head of the bolt. So you can use the split command and split that surface and have a shape that represents just the underside of the head of the bolt, and you can apply it just to that area. That is critical when you're looking at setting up a simulation that mimics the real world. You've really got to watch out for that. You want to make sure your model is fully constrained. You don't want parts that can move and go all over the place. You want to really look at your reaction forces, and you want to constrain carefully. You can constrain it in such a way that the simulation will not work because it can't apply the force, or it looks like it's going to pass all your tests and really it could fail. So you want to watch out for things like that. Looking at the loading types, again, you've got force loads for faces, edges, vertices. You've got pressures, bearing loads for cylindrical faces, moment loads for faces, body loads. Again, gravity, if you're ever in doubt if gravity has an effect on it or will have an effect, go ahead and specify it. You can't go wrong by specifying gravity. And then remote forces and loading. While we do have access to display the first and third principal stresses, a lot of people are more concerned with the von Mises, and in a sense that's kind of a summarization of the first and third. It's kind of a combo, so a lot of people look at the von Mises stress, which is what you saw in the hitch just a minute ago. The contacts, we reviewed that pretty quickly. You have bonded, you have separation, sliding, no separation. All of these different types of contacts you can do and apply either manually or automatically. When the analysis starts to run, it will, or when the mesh starts to run, it will try to apply those throughout your entire assembly. And it will give warnings if it finds any problems with any contacts, if it sees that a contact cannot be applied between two faces because of the contact settings, because of the simulation settings we looked at. You know, the gap may be too great and it can't put a contact between those two faces. It will give that warning. Again, you can simplify your assembly with a level of detail, excluding parts. You've got your automatic contacts, apply your loads and constraints, run your analysis, and review the results. Now, one thing we didn't look at, when you review the results, you're not stuck with just looking at this interface and your color bar. By the way, you can tweak your color bar, you can change the colors of it, you can also specify a maximum and minimum. Right now it's based on the analysis. So if I specified my maximum at 1/8 of an inch, not that one, if I specified it at 1/8 of an inch, you're going to see the dividing grades in the color bar change, and you're going to see the colors of the assembly change. So now there's less red. If I come in here and set the color bar max to 0.06 flat, then you're going to see a lot more red, such as on the trailer hitch ball itself. So you can tweak those settings to get the best fit for your situation. Control over the shading. You can also animate this to see how this thing is actually moving and deflecting. You can speed up the animation, slow it down. You can record it out to a video file and share it either internally or externally. But also, not just looking at these results on the screen, you can send this information out to a documented report. You can give it a title, who created the report, who ran the analysis. You can choose the size or the resolution for the images because it's going to include a screenshot of your von Mises, your principal stresses, your displacements, your strains in your equivalent planar directions. It's going to include all of that as part of this report. And of course, give it a file name, a location, what types of property information you may want to include, such as the materials of the models that were used, part number, stock number, description, things like that. What simulations you may want to include, what kind of contacts were included or used, and then what format it's going to go out in. Rich text file or an HTML is pretty much the default. So when I say OK, it goes through the process of taking those shots, sending this out to an HTML, and generating that report. Takes just a few seconds, and then once you have that, you can take that report and send it out to anybody you want to inside the company or outside the company, your choice. So when it gets done, then you'll see the HTML file pop up on the screen. You've got your stress analysis information at the top, some of the project info next, and then some details about the simulation. It was a single point, static analysis, and when it was ran. That is very critical to a lot of people. They want to know, okay, we made a change on this date. Did this simulation take into account that change we made? And you can trace that back with the date it was run. You've got your mesh settings for anybody who wants to get into the nitty-gritty of how this simulation was set up. You've got your material property information that was used. Then your operating conditions, such as gravity specified, where gravity was located. Gives you a couple of shots of that so you can see that. How your forces were applied gives you a couple of shots to see that. Force number 1, force number 2, you can see highlighted in blue is what it's showing you. And you can click on these and see a larger image, get better clarity. Then you've got your constraint location so everybody can access and see that. You've got your contacts that were specified. You see the parts that had the contacts specified or applied to them. Your reaction forces and the results summary and the result images. So now you can come in here and look at the actual von Mises and say, okay, there's where the high stress is, there's where the low stress is. You can come down even further and look at the deformation and any safety factor violations. So the report's a pretty nice conglomerate of all that information, one massive location to get everything you need, all the access to the information you might need. Looking at convergence, you want to run a certain number of tests or refinements when you're working in an analysis. The convergence deals with a P refinement or an H refinement, and you can change how many tests to run to get more refinement. With the convergence plot back in the simulation itself, you can see that convergence only ran one test and only two sets of convergence. This will take a little bit more time. If I come in here and I tweak the convergence settings and I change the H refinement to say 5, well, this analysis when I ran it a few minutes ago, it only took a few seconds. But if I change that to 5, it could take 5 minutes, 10 minutes, however long it's going to take to run through all of those refinements. So that can definitely increase your time, but it also gives you more confidence in your analysis and in your constraints and your loading, so that you know whether or not this thing is really going to fail like you're predicting it will. You have to watch out for stress singularities where the stress is rising suddenly and very highly for no explained reason. That can be related to the mesh itself. You might want to have to go out in there and refine the mesh a little bit. A lot of causes of stress singularities is your loading or your constraints have been applied to the wrong types of geometry. It also could be the wrong type of load or wrong amount of load. I've seen that happen where somebody thinks it's going to be a 4,000-pound load and they just typo it and put 41,000 or 40,000, and they're like, whoa, 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 this is wrong. typos happen. But also any kind of inside corners, situations inside the model that aren't really physically possible for us to see a loading condition or a constraint condition in that area. Fillets can also create stress singularities, whether they are there or even if they are not. You may have suppressed a fillet that you actually need because it could have some kind of impact. Thin wall bodies, I said we'd come back and talk about this. You can do thin wall analysis, but you want to look at the length versus thickness ratio. There's no real good numerical value to say, okay, if that ratio is 0.5 or 0.2 or 0.1. You just have to kind of look at the situation. When you set up the constraints and the loads and you run that analysis, what do those results look like? Does it look like the thing is warping or getting bent out of whack further than what it should be under that loading condition? You're going to have some idea. I mean, this is going to be stuff you're familiar with. You're going to have some expectation of how it's going to perform. So you want to watch out for that ratio. If it's too big, then you may not want to use Inventor because it could give you some incorrect results. With the modal analysis, we're going to be looking at the natural frequencies of a system or a component. Systems will have a lot of different natural frequencies, different harmonics, especially for the various components that are used in it, and those harmonics can highly contribute to the failure of that assembly. You've got to watch out for that. The loading and constraints can impact your natural frequencies in a lot of situations. Real quick on the frame analysis, it works different than your FEA. When you look at, if I jump back over here and look how this has been meshed, you're looking at the overall geometry. You're looking at the tubular frame. You're looking at the plate mounts, the brackets, and you're seeing the surfaces divided up into triangles. With the frame analysis portion, it doesn't use that same kind of mesh element. Instead of using the elements, the triangular elements, or brick elements if you want to say that, it uses beam elements. And another term you can substitute in here is a skeletal element. In a sense, you're looking at a point-to-point line to represent that beam. You can simplify and speed up the analysis of the structures. They need to have the same or uniform cross-section size. That helps out big time. It's best for small structures. Like I mentioned earlier with the frame generator, you're looking at doing small things like an overhead crane system or conveyor system or the framing for a piece of equipment, not necessarily the framing for an office complex. If you need something for the larger structures, the more complicated structures, then there's a product called Robot Structural Analysis for that. It's catered a little bit more towards the architectural side of the house, but there is a product that can do the larger structures. And this is what the framing analysis would look like. You're seeing the skeletal or the beam elements. You're seeing the various loading conditions applied and how the stress is reflected. So it looks very much the same as far as the results. The only change you're really experiencing is the elements that are applied to it, how those look and how they behave. So on a quick review, looking at Inventor FEA, where does it work best? Where does it not work best? Just want a reminder that it makes a lot of assumptions when you're doing FEA with Inventor. Your loading needs to be static and it needs to be applied slowly, so no sudden or impact loading situations. The temperature should have no effect on the material properties or the geometry. Those two right there are huge. The deformation needs to be small. You got some flexibility on that one. And no buckling in the part of the assembly. That's actually a pretty big one as well. So you need to look at those assumptions. If those assumptions don't fit what you're trying to solve, then we have other simulation solutions for you. So looking at this chart, we're starting in Inventor Pro. And again, that's linear only, static stress, parts and assemblies. Above that, we get more advanced simulation capabilities. We have the Nastran NCAD, which will do linear and nonlinear. It has some limited dynamics, has a simplified contact set, and it can compensate for some thermal. Above that, we have simulation mechanical. Again, it will do linear and nonlinear. It has a much broader range of dynamic simulation, a much more advanced contact set. It will do thermal and also mechanical event systems, movement inside of your assembly. If those will not fit the bill, we also have Simulation CFD, which focuses more around fluid and thermal flow through a system or through an environment. You can do coupled thermal and fluid, so heated water versus cold water, which also gets into your mixing at the bottom. You can see how those two fluids will mix and change the temperature dynamic through that system, as well as free surface simulation. Now, because you're attending today's webinar, there is a special promotion, and I'm going to let Jeremy Stefanik talk a little bit about that.
Hello everyone, just wanted to let you know that anyone attending this seminar today will receive a discount off any of the higher end simulation products through the end of January, and that is a 25% discount. And if you have any questions, please feel free to contact your local account rep. Back to you.
Thanks, Jeremy. I appreciate that. Okay, so with regard to learning how to use Inventor Professional or any of your Autodesk products, Hagerman and Company is an authorized Autodesk reseller. We have authorized training centers, or ATCs, around the country. You can really gain an advantage by taking classes from us, and especially from the ATC centers. You get more focused, more hands-on, and more one-on-one instruction. We intentionally keep our classes smaller so that we can focus more on each student. Instead of being in a class with 50 people, you're in a class of 5 or less typically. Some of the learning tools you have inside of the software, of course, you have the help system. You have Autodesk 360, where they have some tutorials and information out there. We also offer e-training through us. We have web-based training, face-to-face training. It can be book-driven or custom book-driven or custom training on either of those. So it can be just pretty much standard widgets and things like that, or we can customize it to your exact systems, your exact need, your exact product design and specifications of what you're looking to do. Some of the customer benefits from being on Autodesk maintenance subscription. This is your subscription renewal. You get upgrades to the latest software. You get more cloud computing. With the cloud computing, something we didn't have time to get into was the Inventor optimization. Briefly, what optimization is, and just to show you, that is this little guy here. When you're looking at a piece part is where it really comes in to play. Looking at a piece part on the environments, you have the optimization command. With this, you can set up different material thicknesses. So if you know this thing is going to be an eighth of an inch, or you also want to test 3/16 and a 1/4 inch and 5/16. You want to see which one of these is going to be your best fit and have the best weight distribution and the best strength. You can use Inventor optimization, and it is cloud-based. You set up your materials, you set up your constraints and your loads, and when you hit go, it goes to the Autodesk solvers out in the cloud, and you can continue working. Depending on what you've got set up, it could take a couple minutes to whatever, 30 minutes, 40 minutes, depending on what kind of loading situation you're looking at. It could take a little while to run. So you're able to minimize it, let it run in the background out there on the cloud, and keep doing your normal work. It doesn't stop you. Whereas the full Vault FEA, you've got to wait for that analysis to be done before you can start doing anything else in Inventor, because it's using the local solver, whereas the optimization wizard is using the cloud solver from Autodesk. I think now is probably a good time to look at that second poll question, and that is, do you have analysis needs that can't be met by Inventor Pro's stress analysis environment? Now, there's a lot of options with this one, so read each one of them carefully. We've got, yeah, you need to solve nonlinear problems, or yes, you need to solve heat transfer, yes, you need to solve dynamic problems, motion problems, yes, you need to solve fluid problems, or no, Inventor Professional currently doesn't meet your needs. So I'm getting about 30% voting results. I'll let it go a little bit longer. We're almost up to the 50% mark. Seeing some good response. out of this, seeing quite a few of the no Inventor Professional currently meets our needs, and that's good. I'm glad that a lot of you are in that situation. You've got a broad range of tools you can use and a broad range of capability from Inventor Professional. So we're about at 70%. I'll let it get around 80% and I'll probably close the poll. Getting pretty close. About 20% of you, you need to solve nonlinear problems. That's not surprising, getting into a lot of the nonlinear materials. Even steel and metal itself can be nonlinear beyond a certain point. And Inventor fits the bill up to that point, and then once you go beyond, you need to look at one of the other Autodesk simulation packages. So we're almost at 80%. I'll go ahead and close out this poll and share it with everybody, just so everybody can get a view of what it looks like. So again, about 58% Inventor Professional currently meets your needs, and that's good. I'm glad to hear that. Some of the others, you need to do more dynamics problem solving, more nonlinear. We do have the other products that might better fit your need for that. So thanks everyone for responding to both of those polling questions. I think at this time we'll go ahead and stop the presentation. We're going to continue to take questions in the background. If you have any questions, just feed them into the Q&A section. I know Forrest has been working vigorously to get all of those answered. We will address the questions as best we can. If there's something that you ask that we need more information on, we may want to do a one-on-one call with you later, so we might arrange something like that. If you need to see a more detailed demonstration of Inventor FEA, something maybe more tailored or suited to what you're doing, we can certainly arrange that. Just contact your Hagerman sales rep. Otherwise, thanks for attending today's webinar, and y'all have a great week.
Thanks, everyone. As Kendra mentioned, we're going to stay on the line for a few more moments to help answer questions. If you need to drop off or if you think of a question later this afternoon, you can reply to the confirmation or the reminder email you receive from GoToMeeting, and we can route those to the appropriate parties to get your questions answered. Also, as a reminder, you will be receiving an email link an email containing a link to the recording of today's presentation. And when you log off, you'll be prompted to fill out a short 3-question survey. We ask that you take a few moments to do that. So thanks, everyone, for attending, and have a great day.